Finite element analysis is a method of structural or stress analysis using a different set of numerical methods than what you find in most engineering courses. The name finite element analysis is based on the fact that your structure is basically broken up into pieces called elements, and then the numerical methods are applied to each piece to solve for displacements, stresses, and strains. In this video, I'd like to provide you with some basic knowledge of how finite element analysis is used for structural analysis problems in engineering. Before we get into the basics of finite element analysis, be sure to like this video and subscribe to this channel so you can stay in the loop about advice and concepts for engineering careers that will help you to be successful. So in a nutshell, finite element analysis is where you take a structure and you break it into pieces, and these pieces are called elements. And so the purpose of this is that you're trying to formulate a model so that the loads, stresses, strains, other phenomena, they also do this with thermal, which we'll get into later, but for mechanical loads, stress, and strain, it gets calculated in each piece so that you could see sort of where the stresses are in the model. So there's a number of different types of elements, and in this kind of simplified model down here, the bracket is modeled using a bunch of rectangular shaped plate elements. It might not look like 2D, but because this is with the thickness of the 2D turned on, you got 2D elements that have a thickness assigned to them, and you could turn it off or on. But that's what a plate element is, and it basically calculates it using the plane stress equations. And so that's kind of a summary of how plate stresses and plate elements are used in finite element analysis. And we might model fasteners using a different type of element, and in this case it shows a bar element. So we got the plate elements and then fasteners modeled using bar elements coming from the bottom of the plates. And so this is how we capture the behavior of fasteners, with these bar elements having different types of phenomena, like different type of axial stress that you might expect from a bar, or different behavior for bending stiffness and such than a 2D plate. And then they do have constraints on this particular node on these bar elements so that it stays in place, and then this load applied right here. So this is a good simple example of a finite element model. And so each of these elements, just to go a little bit deeper on that, so there's a number of nodes assigned to it. So in the case of a plate element, you got 4 of these nodes, and then this is attached to other plates, of course. So a plate right here would share this node. So a plate element usually has 4 nodes, at least a basic one does. And then a basic bar element has 2 nodes, as you could see here, just in order to make its shape. And then nodes also are how sort of the software in the background, or the hand calcs that you're doing, how you calculate the change in position of each of these nodes so that the element can capture its stresses and strains and such, because if you change the location or position of these nodes, it is going to change the shape of the element. And from there, that's how the software calculates stresses and strains and whatnot. So when we take these plate elements that we first have, we'd first assign a plate property, so that way we can say what the thickness of the plate is. So if the thickness of the bracket is 0.1 inch thick, we'd assign plate elements that are 0.1 inch thick, and then assign a material to it with its Young's modulus. With, in some cases, you'll add like a yield strength if you're doing nonlinear, but adding material properties basically to capture the correct deflection that you're looking for, the Poisson's ratio that would also show certain strain values and phenomena and such. And then for the bar elements here, which represent the fasteners, we can assign a shape which in this case is a circular bar representing the diameter fastener, and then correct fastener materials. And fasteners are going to be more nuanced just because of different properties of them versus a regular circular beam. But whatever you on your team determine that the properties of the fasteners are is what you're going to assign to these fasteners. And note that, because these are circular in this case, because fasteners are basically circular shaped, but in this case that I showed you earlier, it's a square shaped, so this would be better for showing a square bar or a square beam. But yeah, you just make it whatever shape it's supposed to be for whatever it's supposed to represent. So after we build our model and use these other types of elements, so we'll apply loads and constraints like we mentioned over here, and then the material properties and everything else that we already did. So then that's how the software or your hand calcs calculate the stress and stiffness related properties. So for the bar elements, which represent the fasteners, we can assign a shape, which is the circular bar, and then we build our model using these or other types of elements. Then we apply the loads and constraints, and then the stresses in the model can be calculated. So like I mentioned, nowadays this is mostly done by a software. Technically, the process was developed as a hand calc using stiffness equations, and nowadays this would take forever to calculate all these stiffness equations and displacements and stresses for all of these elements. So that's why nowadays we have software for it. And each different type of element has its own complex set of equations for stiffness and such. And like I mentioned, for plate elements, it's plate stress or planar stress as well. And then for bar elements, it's going to use more of like the axial loading to calculate axial stress, shear loading to calculate shear, as well as bending depending on the length of the element and such. And this is the general equation. This is the force equals stiffness times displacement. So displacement and then stiffness is in the form of a matrix for each type of element, and each element using its own stiffness equation in there. So the software uses systems of equations to calculate forces and stresses in elements based on the applied loads and the element stiffnesses. So it actually does, it's kind of backwards from what we do with basic hand calcs, where we apply the load and then calculate the stress, and then if necessary calculate the strain, and then if necessary calculate the displacement. The way FEA works is actually using systems of equations to calculate first the displacement of the nodes, and then after the nodes displace, then the element changes shape, you're able to calculate the strain from there, and then you're able to calculate the stress from the strain. So that's basically how the background process is going with these finite element analysis solvers. So there are a lot of other types of elements. We only covered two here, just bars and plates pretty much. And there's also a lot of other ones. There's solid elements, which is pretty much the 3D version of a plate element. So this is not going to be plane stress or plate stress. It's going to be 3D stress, where you got normal stress and shear stress in all degrees of freedom. Then you got beam elements, which are pretty much the same thing as bar elements, but the cross-section can actually vary along the length. In this case, we don't have the cross-section varying along the length. These are bar elements. And then spring elements, which pretty much the element acts like a spring in a few different degrees of freedom, and you just directly assign the stiffness in each degree of freedom. There's tons of others that is out of the scope of this training, but just giving you a brief overview of that there is plenty of different types of elements that may be used, and it's up to the analyst to decide which elements are going to capture the behavior of the model best in this particular case. So there's also a lot of other types of analysis, because the one that we're showing here is just a simple statics problem where you have a static load and it's fully constrained, and so it's a statics equation. There's other types of analysis that are done in finite element analysis. You might have thermal, so in this case, instead of doing mechanical stresses and whatnot, you're dealing with you might apply temperatures at nodes, or you might apply heat influx at nodes or elements, and then the model is going to calculate heat transfer within it. So, like for instance, if we had assigned instead of a force here, or if we had either assigned a temperature at these nodes or just also assigned that, then it would calculate what the heat transfer and temperatures are around this entire model, or a heat influx, then calculating the temperature around the model and the heat transfer around the model and such. And there's also dynamics, where you're dealing with applying acceleration or variable loading to the model and assessing dynamics behavior, like acceleration at certain nodes and modes at certain nodes and such. Buckling, which if you know about that, it's like if a tower kind of changes shape under compression. That's where you're finding eigenvalues related to the instability of that, where the structure in compression just changes shape, changes deformation behavior, and potentially collapses or fails due to that. There's also solvers for that in FEA. So yeah, that's our brief overview of FEA for today, and definitely let me know if you have any questions or further resources that you'd like to be directed to about how to learn this, or questions about how to break into the field or succeed in it. And if you found this video helpful or liked it, I invite you to give it a thumbs up and subscribe to this channel to continue getting more advice and learning more about engineering careers and how to be successful in them. Thanks for the view. Look forward to talking to you soon. Bye.